This is Atwood's machine. It consists of two masses, so M1 and M2. The masses are connected by a rope, and the rope goes over a pulley. So in this example, say if M2 was more massive than M1, then M2 would go down and M1 would go up, as shown in this picture. So now I will show you how to solve this problem for Atwood's machine. Let's find the acceleration of the system and the tension in the string. Okay, let me get rid of this first. First, let's draw a free body diagram for each of these objects. Oh, well, it looks like this, okay? This, so we know, it's like this. We've got M2, this is M1, and the forces acting on them. We have force of gravity here, force of gravity 2, which is M2G. This one also, force of gravity 1, which is M1G. And then there's a tension. So the tension is the same. It's the same throughout the rope. So if M2 is larger than M1, then M2 is going to go down. It's going to accelerate. So it's going to go, so this is the acceleration. It's going to go there, and this one's going to go up. But they're both going to have the same acceleration because they're connected by a rope, so they move together. So first thing we do is to draw the free body diagrams. So for M1, and they said M1 is 5 kilograms. So we got force of gravity 1, which is M1G. We have tension going up like that. Actually, did I do that right? Is force of gravity 1, does it have a larger magnitude than the tension? If it's accelerating upward, the net force has to be up, right? So I drew this wrong. I made the force of gravity too long, and I made the tension too small. So like this. So tension needs to be larger than the force of gravity if it's going to accelerate upwards. Net force has to be up. So that's the free body diagram for mass M1. Now for mass M2. M2 is 10 kilograms. So this one, we got the force of gravity 2, which is M2G, which is going to be twice as large as M1G, because the mass is twice as large. So I'm going to try to make it twice the size. So this is Fg2 equals M2G. And the tension is going to have the same length as this one. So that's the free body diagram. Now we apply Newton's second law to this free body diagram. For this one, of course, let's put the acceleration. The acceleration is this direction on this side and this way on the other side. So let's do it. Apply Newton's second law for mass 1. I'm going to say up is positive, since the acceleration is up. I just do that for convenience. You can also choose down as positive. So sum of forces in the y direction is T minus m1g. And that equals mass times acceleration, m1a. Do the same thing now for mass 2. This time I will say acceleration, or I'll say down is positive, because the acceleration is down. So sum of forces y equals m2g minus tension, and this equals m2a. So here we have two equations with two unknowns. So I just have to solve. So I'll solve this equation for tension and put that into this equation. So tension equals m1a plus m1g. Put this tension into here. Then I get an equation just with acceleration. m2g minus this thing, minus m1a minus m1g equals m2a. I gotta get the a's all on one side. So I'm gonna add m1a to both sides. That will get rid of this. So I have m2g minus m1g equals m1a plus m2a. Let's take out the common factors. Common factor of g on this side. Common factor of a on this side. m2 minus m1g equals m1 plus m2a. Now we divide by m1 plus m2. m1 plus m2. m1 plus m2. So these things cancel out. So we are left with a equals m2 minus m1 over m1 plus m2 times g. Now you can see, if the masses are equal, the acceleration is going to be 0. If m2 is greater than m1, acceleration is positive. That means it's going down. m2 is going down. If m1 is greater than m2, this thing is going to be negative. That means that m2 is going up. So once we get this a, put this a into this equation, and then we get what t is. So let's do that. So t equals m1 times the a, m2 minus m1 over m1 plus m2 times g plus m1g. Well, we can make it look really nice. Just get a common denominator. Tension is the same on both sides. Doesn't matter what the masses are. Tension in the rope is same throughout. So let's get a common factor, common denominator of m1 plus m2. I'll take out the factor g. So I'm going to multiply this thing. I'm going to multiply this by m1 plus m2 over m1 plus m2. So both sides have the common denominator of m1 plus m2. Now look here. m1 times m1. m1 times m1 and m1 times m1. But we have negative, positive. So actually, this thing is going to cancel out. This term and this term cancels out. So we have m1 times m2 and m1 times m2. So that's 2 m1 m2. So it becomes tension equals 2 m1 m2 g over m1 plus m2. So this is our expression. So we have the tension and we have the acceleration. Now, I did a lot of algebra there, so it may be easier for you if you were actually doing this problem. It may be easier just to put in the numbers. Put in the numbers for A. So let's put in the numbers for A. So we would have, put in M2. So M2 is, so A is going to be M2 minus M1, so it's 10 minus 5 over 10 plus 5 times 9.8, which is 5 over 15 times 9.8, which becomes, did anyone work that out? Is it 3.27? So it's 3.27 meters per second squared. So that's our n for numbers. Now you could just take this number and put it into here if you wanted to. But I worked it out using the algebra. But now we can take, put in the numbers for the t. So t is going to be 2 m1 m2. 2 times 5 times 10 over 5 plus 10 times 9.8. So that's 100. 100 over 15 times 9.8. Is that right? Did anyone get a number? $63.3. So it's 63.3.
It's 65.3.
65. 65.3 newtons. Okay, so that's, so there's the number. Okay. Are there any questions? I don't know how you got the T equation. So the T equation, I just took this. This is T. I took this. So A is given by this expression. I put this in for A. So this is the A here. And then I found the common denominator. Common denominator is M1 plus M2. So I multiply this thing by M1 plus M2 over M1 plus M2. That's just 1. I can always multiply by 1. And then I cancel some things out. So this is M1 times negative M1 squared. This is M1 times positive M1. So negative M1 squared plus M1 squared gives me 0. So these two terms cancel out. I'm left with M1 M2 plus M1 M2. So it's 2 M1 M2. That's how I did the T. Up is positive for M1 and down is positive for M2. That is correct. Okay, that's Atwood's machine. Any further questions? Oh, why did you do that? Why did I say up is positive for M1 and down is positive for M2? Why did I say that? I said it because M1, the acceleration for M1 is up, and the acceleration for M2 is down. It just is convenient. I can write it, I can always put positive for the, so I can put positive A on the right side. It just makes it a little simpler. You don't have to do that, but I like to do that. Okay, so let's stop here. Yes, you are. Yes. You can have, yes, I should say the question. You are allowed to have different directions for positive for the same problem, as we did here, as we did on the previous problem, where positive, from the previous problem, positive was in the horizontal direction, for the mass on the table, and it was in the downward direction for the mass hanging down. So we can have different directions for positive.